questions left over from yesterday? Okay, so just to remind you where I was, so I was just saying a little bit about classical many-body chaos, and in particular, talking about this situation where we have a one-dimensional system which is classically chaotic, so nonlinear local interactions, say between spins or some anharmonic oscillators or something like this, so that this is a classically chaotic system. And then we consider two initial states which are differ only on site 0, and they will then evolve chaotically, and the difference between them will grow and spread. And then we measure the magnitude of the difference between them by this, the difference at x and t divided by the infinitesimal difference at space-time origin. This thing inside the Lieb-Robinson cone grows exponentially. And so if we go away, so here's space and time, and this is true, I put a vector on there because this is true in more than one dimension. If we go away from the origin along a ray at a given speed, v, what you find is that the growth of the difference between the two states is exponential, or it's a decay, right? If you look inside this Lieb-Robinson cone here, it's a growth, and outside it's a decay. So you have this Lyapunov exponent, lambda v, a velocity-dependent Lyapunov exponent, which is a function which is positive at 0 speed, goes through 0 at the Lieb-Robinson speed, and then is negative at higher speeds. Right. Okay. Now, if we don't do a chaotic model, but we do some non-chaotic integrable classical model, what you will find is outside of the Lieb-Robinson cone, it will exponentially decay, but inside, you won't have the exponential growth because integrable systems don't have that instability towards exponential growth, and so you get the Lyapunov exponent is actually 0 inside the Lieb-Robinson cone and negative outside for integrable systems, classical integrable systems, probably for quantum integrable systems too, and we have some examples of that. But this, so far, I don't know of any calculation of out-of-time ordered correlators for a really interacting quantum integrable system, a beta-ansatz solvable system. I don't know if anybody knows about any such thing, but I'm sort of asking around beta-ansatz people whether they can do that calculation or whether anybody has done that calculation, because I'm collecting the behavior of lambda v for all sorts of different models. Now, if we just take the same classical model and instead of giving it an infinitesimal perturbation between the two states, give some small non-zero perturbation between the two states, it'll also grow exponentially until it becomes of order 1, and the two states will then just be different. They won't remember that they were similar at all. And so what you get, if you don't start with an infinitesimal perturbation, you get the perturbation saturates, and inside this shaded region here, the two states are just completely different. They don't, you can't tell by looking in here that they were anything similar at the beginning, right? And so this is the region you might call well scrambled. Okay, so for non-infinitesimal perturbations, chaotic systems will scramble, forget their initial condition within the Lieb-Robinson cone. And this recent paper here from a group in Bangalore demonstrates this for the classical Heisenberg spin chain. The classical Heisenberg spin chain is a chaotic system. Now, if you do a fully quantum system, so when I say fully quantum system, what I mean is not a large n or a semi-classical model, a model which only has 2 or 3 or 4 or 5, some small number of states per site and only has short-range interactions, so the local Hilbert space is small. such as 2 states per site, spin a half chain, there you can't make a small initial local difference, right? The smallest difference is a quantum, right? And it can't be small, and if your spin a half, it's of order 1, right? And there's no room for it to grow any bigger. And so this regime of positive Lyapunov exponent in a naive thing like an out-of-time ordered commutator doesn't seem to be there for spin a half chains, or maybe we don't know how to define it. But outside of the Lieb-Robinson cone, you still have a negative Lyapunov velocity-dependent Lyapunov exponent outside the and I'll say a little bit about that in a second. And so you can still define the Lieb-Robinson speed as where the Lyapunov exponent goes to 0, provided you're coming from outside the Lieb-Robinson cone. But inside, it's not yet clear how to define the Lyapunov exponent for quantum chaos. And it's not even clear yet that there is a well-defined Lyapunov exponent for quantum chaos. But if you go to like a large N model like SYK, or you go to a semi-classical regime, then you can define a Lyapunov exponent for quantum chaos. But the key is there that you can just start with a small perturbation, and there's room for it to exponentially grow so that you can see its exponential growth rate, right? But if you don't have a big Hilbert space, there's no room for that. And so we don't yet know how to define the Lyapunov exponent. OK. So now that's just some comments about classical chaos, classical many-body chaos, which is stuff that has been known for a long time, but it doesn't seem to be widely known at all. I didn't know about it until 2 months ago, just because I hadn't paid attention back in those days when people were doing that. OK, but now I want to get back to quantum systems. And so before I was talking about entanglement dynamics of states, but now rather than talk about states, I'm going to talk about operators. All right? So not look at the properties of states, just look at the properties of operators under the Heisenberg dynamics. Okay? So this is operator spreading dynamics. And so what we do, as I said yesterday, is start with an initially local operator. So say something at position 0 times 0, that's right. So it's some non-identity operator, which has 0 trace at the space-time origin site, and it's the identity at every other site, right? So it's just a local operator, and it's not the identity. And then we time evolve it with our time-dependent Hamiltonian, or our unitary time evolution operator here, to whatever that operator becomes at later times. Okay? Now, in the spatial regions where this operator is just a product of identities, nothing happens, right? Because a unitary operator times the identity times U dagger identity U is the identity, right? And so the dynamics, the identity operator is, as we well know, is a very special operator. And it's a special operator in the sense that, in this sense, it has no dynamics. It's an eigenoperator of the dynamics for any unitary, right? It's really the only operator. If you take a generic system with no conservation laws and nothing special, that's the only operator which is it's just gonna not do anything. But the part of the operator that's not the identity will do stuff, and it'll spread. Okay, and let me just draw that picture, show you what that looks like. And it'll spread within a Lieb-Robinson cone. And so basically, so here's a picture of space, time, and the operator started somewhere back here, and it's been spreading at the Lieb-Robinson speed. And inside of the Lieb-Robinson cone, the operator is locally not identities. It gets scrambled by U of t into some complicated operator, right? And then, but outside, it's still almost purely identities. There's actually, in general, there is some weight, small, exponentially small weight of the non-identity part, which falls off with the Lyapunov exponent, which is now negative, outside of the Lieb-Robinson cone, right? So basically the operator, what it looks like is approximately a non-trivial, highly entangled, scrambled operator within the Lieb-Robinson cone times the identity operator outside the Lieb-Robinson cone. But this is approximate, near the boundary. It's not a sharp boundary, and outside here, where it's not absolutely purely the identities, it's only the identity up to exponentially small tails in general. Unless we have a strict speed of light or causal limit, and then there can be another line, or maybe the Lieb-Robinson, some cases the Lieb-Robinson speed is the speed of light, and outside there's strictly zero information getting. Or there could be a second speed here which plays the role of the speed of light, beyond which everything is strictly zero, right? The Lieb-Robinson is not a strict causal limit, right? There can be these exponentially small influences outside of it. It's just they're decaying, right? Okay. Okay, so do this a little more systematically. Let's say we have any. Let me just pause. Any questions about that?
Could you repeat your definition of this Lieb-Robinson velocity?
Well, it's basically defined here that inside of the Lieb-Robinson cone, the operator is far from the identity, the locally. This is almost a definition of it right here. The operator spreads, and outside of the Lieb-Robinson cone, its non-identity part has a weight which decays exponentially with time, with this decay rate which depends on the speed, and that decay rate goes to zero at the Lieb-Robinson speed. This formula is in the abstract of Lieb and Robinson, right? They call this thing mu. So it's really, the best thing to do is go outside the Lieb-Robinson cone, ask how much non-identity weight is there in the operator locally at those positions. It decays exponentially. Look at the decay rate. It's exponential. It's a function of the velocity. And then ask what velocity does this decay rate go to zero? And that's the Lieb-Robinson speed. Now there's the Lieb-Robinson bound, which is an upper bound on that speed that they proved, right? But I'm taking, the physical thing they were bounding is this speed, right? And they were able to get an upper bound on it, which I think in general is not a tight bound, but the concept of the speed is there in the paper, and I think we should view that as the physical thing, right? Of course, the bound is mathematically how tightly can you bound it. Yeah?
So when you say weight, does it mean some sort of a norm? Or?
Yeah. And I think it doesn't matter much exactly which norm you choose. I'm going to pick a norm in a second, I think. Yeah, there's my inner product. So more systematically, right? Worrying about things like that. Okay, so let's take a spin-a-half chain. A spin-a-half chain has 2 states per site, which we could call up and down. And therefore, it has 4 local operators per site, which are the Pauli operators, 1, x, y, and z. All right? And when we study operators, we can just view the operators as states on a doubled system, right? So a state looks like this, right? It's a linear combination of a set of basis states, right? And let's say these basis states are just the eigenstates of up and down at each site. And so this is the matrix product way people write these things, right? So each one of these little lines here, we feed in an up or a down. That's 2 states per site. These are the sites. And then the whole graph here is this coefficient Cn, right? So Cn is represented by this whole structure, and it has as inputs is the spin up or down. And those are all the basis states, right? Whereas an operator looks like this, instead of having 2 to the, if it's length L for spin a half, instead of having 2 to the L coefficients, it's got 4 to the L coefficients, right? Because it's got a bra and a ket, or I guess, and these coefficients B and M, there are 4 to the L of them. And so you just draw it like this, where you put the bra in on one side and the ket in on the other side. And so each site now takes in 2 states, right? The column and the row of the matrix. And but you can just then view the operator as just like a state in a Hilbert space, which is bigger. It's the square of the original Hilbert space. Right? And then you have super operators which operate on these operators. Right? So you just go up one level. Okay. Now, right. So now the natural basis here is, here we've got the natural basis for the states is up or down on each site, just a product states, and similarly we can just use the Pauli operators as a natural local basis for the operators, and then we can just make product operators, and we call those Pauli strings. Right? So a Pauli string is just a string of outer products of Pauli operators. Right? So here's one, it's Y on site 0, it's the identity on site 1, it's Z on site 2, etc. Right? And there's 4 to the L such basis states for the operators. Okay, and then a natural inner product with the way I've done it here is to take, so the product of operator A and operator B would be A dagger B divided by 2 to the L trace. Take the trace over the whole thing, and that's the inner product, so that gives the norm. And then, of course, states evolve like this. A state U acts on the state, produce the initial state, produce the final state. And for a generic dynamics here, this contains nothing for U to naturally cancel against. So there's no locally, in a generic case, there's no locally simple states that just have locally simple dynamics. Right? Now, of course, you have certain Hamiltonians where there are special states which have no dynamics because they're locally eigenstates, but that's not true for a generic type of Hamiltonian. Whereas with operators, the dynamics is like this, right? And because it's U dagger U, you have no local dynamics if locally the operator we're talking about commutes with the Hamiltonian that's making the dynamics, right? And in particular, the identity commutes with everything, so the identity will always have no local dynamics under this dynamics because U dagger can just cancel U, right? And if you have simple conservation laws, you can also have other operators which have no dynamics. Okay. And so what we do now is we just evolve our operator, right? Here's our initial operator, and let's say it's initially just a local operator on site 0. We time evolve it, and we get this A0 of t. So here what this means, this is the operator that was initially on site 0, but now we're asking what it looks like at time t, right? And then we take that and we expand it in terms of these Pauli strings, which are just products of local operators, right? And so it's just the normal thing you do with a state, right? You have a basis and you expand it, right? Now, let's normalize the initial operator to have, I should have put a 2 to the L here, so there should be a 1 over 2 to the L here to be consistent with what I wrote on the last page. Let's normalize it to have norm 1. And then under time evolution, the norm of the operator is conserved, right? Because if I put in the UU dagger here, they all cancel in the trace. And so the norm is conserved under unitarity. And so just like any state, the sums of the squares of these amplitudes is conserved, right? So that unitarity is a conservation law, but that's just preservation of norm. Right? Preservation of norm can be viewed as a conservation law because dynamically it's something which is conserved, right? It doesn't change, right? And I'm going to use it as a conservation law for something that's actually moving in a second. Okay? In fact, that's what I'm going to look at right now. Okay, so now let's look at so this operator is going to spread, and let's look at the dynamics of the edge of the operator, right? So that's which is moving at the Lieb-Robinson speed, and here's a set of papers doing this for random circuits where you can really do it systematically and analytically. Okay. So as the operator spreads, these weights here, which are the squares of these amplitudes, moves from short Pauli strings to long Pauli strings. That's what spreading is. The operator is getting more and more complex, spread over more and more regions. And when I say the length of a Pauli string, if I have a Pauli string, what it looks like in this case here is on the left, it's identities, and then there's the first non-identity operator, and that's the left end from your point of view, I think, right? And then there's the non-trivial part of the string, and then there's the rightmost Pauli operator, and that's the right end, and after that, it's all identities, right? So when I say the length of a Pauli string, what I mean is the length of the part of it that's not pure identities, right? Okay, and you know, under the dynamics, the operators at the end will tend to hop over to the next site, right? And make the strings longer. So each string has an edge. It's got two edges, the right edge and the left edge, outside of which it's purely identities, right? So in 1D, those are just points, the left edge and the right edge. If we're in more than one dimension, the string isn't a string. It's a product of operators. And the edge is now a surface, right? So it'll be some surface inside of which the operator is not the identity, and outside it's purely identity. And this surface will be moving at the Lieb-Robinson speed outwards. Right? That's the dynamics. And in higher dimension, the Lieb-Robinson speeds don't have to be the same in all directions. Even in one dimension, you can have chiral dynamics where the right Lieb-Robinson speed is a different speed than the left one. But I'll assume it's symmetric, just for simplicity.
One outside, or is this one of these next?
Okay, right. Okay. So the full operator, yeah, that's a good point. When I'm talking about a particular string, I'm talking about a particular basis operator, and then I mean strictly the identity outside. But the full operator will contain strings with exponentially small weight that actually have their edges further out, right? And so the edge of the operator is something with a probability distribution in the state given by this probability distribution here, right? So the exponentially small stuff is, here I mean strictly the identity, but I'm talking about a basis state, right? And then the operator will have the tail due to a tail to other basis states, right? Yeah, that's a good point to clarify. Right, so now in 1D, this is reasonably simple because the edge is just a point, and so we can think of it like a particle, and we can look at the density distribution of the right edge, right? And so we call this the right weight, right? And what we do, so this is the weight of all strings, the amplitude squared. And then we restrict the sum, if we're looking at the right weight at position x, to the strings whose last identity operator is at position x, right? And so that's right weight at x. And then this is a probability distribution here. If I sum this over x, it's 1. And so you have the edge of the operator has some probability distribution, which looks like this. The center of it moves at the Lieb-Robinson speed. This tail is outside the Lieb-Robinson cone, and it's this tail, which is the exponentially small stuff. And then inside the Lieb-Robinson cone, this is where the identity is not 1. And this tail is just the little bit of the operator which actually has its edge back here and is identity inside the distribution here, right? So this tail is actually physically quite different than this tail. But in one dimension, it's just a Gaussian, as I'll say, so they look mathematically the same. Okay, so now I take a particular basis state and let the dynamics operate on it, and I have nearest neighbor interactions. And what will happen is this has amplitudes for making the string shorter, leaving the string the same length, or making the string longer. All of these things can happen unless we're in some large n limit. So if we're in some large n limit or large q limit, you can have the probability of making the string shorter go to 0. And in fact, you can have the probability of leaving the same length go to 0, and then it moves deterministically. So you can go to limits where it moves deterministically. But if you're talking about something where this string, the space of operators is just the 4 Pauli operators, you'll have all 3 of these things happen with some probability. but it's biased to more making it longer than making it shorter, right? If the time step is very short, the most likely thing is just leaving it alone, but the second most likely thing is make it longer, and then making it shorter will be even rarer, right? So you're biased towards longer rather than shorter just because entanglement happens, right? If entanglement can happen, it will, and so operators will get more complicated if that's possible, right? That's the second law, right? So the edge distribution does basically a biased diffusion in one dimension. It's a random walk, or well, it's not a random walk. It's a distribution which drifts in one direction, but also spreads and diffuses because it's doing these both forward and backward steps. And the drift speed of it is the Lieb-Robinson speed, or the butterfly speed. Now, if we go to more than one dimension, now the edge isn't just a point, it's a whole curve, and it's doing some nonlinear stochastic motion model. As Adam Nahum has argued, and I think it's a convincing argument, the coarse-grained dynamics of this will be given by the Kardar-Perzisi-Zhang dynamics of such an object.
So presumably the edge is not really defined as a single point.
Right. Well, that's what we're doing here. It's a distribution here.
So,
Right? It's defined as a single point for each basis state, but then the operator itself is a linear combination of those, and so that gives it a distribution. Just like a wave function. It's like a wave packet for the edge. Right? Sorry, I interrupted you. Did I answer your question?
no, I understand the point. I just, when you're talking about the motion of the edge itself versus the distribution around I was just wondering if technically you define it at the point, or you do some kind of averaging also around the region, around the point?
Well, it's a probability distribution for the edge. Right? So the edge is a wave packet or a probability distribution, and it's evolving under the dynamics, and that evolution in one dimension, the coarse-grained dynamics of that seems to be just bias diffusion. No, the center is not moving. The right edge is going to the right, and the left edge is going to the left. The center of the edge is moving, yes. The center of the operator is not moving. The center of the edge is moving. Yes, I'm sorry.
So, and the spread is diffusive. So
Yeah,
the
yeah.
location is relatively well defined.
Yes, yes. So that's here, right? So when you solve a bias diffusion equation, this is what you get. And the position moves linearly in time, but the width of the distribution is square root of time. So that makes the Lieb-Robinson velocity sharply defined in the limit of large time. Yeah. Any other questions? Yeah. So if we do this in 1D, so this is just bias diffusion, right? And so there's a diffusivity of the edge, right? Which is how this distribution broadens with time. Now, if we go outside the Lieb-Robinson cone, which is this tail here, this is the tail of, which tells you the probability of the operator at that position not being the identity, right? And so we can match this formula outside the Lieb-Robinson cone onto this formula, which I was telling you earlier, this is from Lieb and Robinson, just in a slightly different notation, for x equals vt. And then you can just read off the Lyapunov exponent, which is negative outside the Lieb-Robinson cone, and it vanishes quadratically at the Lieb-Robinson speed, right? So the Lyapunov exponent is negative outside the Lieb-Robinson cone. It goes to 0 at the Lieb-Robinson speed, as expected, but it's going quadratically. And if you extrapolate that past into the Lieb-Robinson cone, it would be negative again, and that's clearly not the right Lyapunov exponent for inside the Lieb-Robinson cone. So in the quantum problems, if there is a Lyapunov exponent which is defined both inside and outside the Lieb-Robinson cone, it's presumably singular at the Lieb-Robinson speed. Whereas classically, it just goes through 0 smoothly, and the Lieb-Robinson speed is just where it happens to go through 0. There's no singularity there. But here, and that's also true for a lot of large N models as well, like SYK chains. Where's Yingfei? Right. Okay. So this again, there's a velocity-dependent Lyapunov exponent outside the Lieb-Robinson cone and at the Lieb-Robinson velocity, but not necessarily inside. Right. Large N, large Q models, semi-classical limit, these kinds of things, you can have this diffusivity go to 0, so the motion of the edge is more deterministic, it could be really deterministic in some models where it's just really moving deterministically, or it could be broadening slower than square root of time. There's various cases, right? Like if you do the KPZ, it broadens slower than square root of time, but it does broaden just as a smaller power than the square root, right? So there's various cases. Now, as I was saying, for the fully quantum, what I call fully quantum, which means order 1-dimensional local Hilbert spaces with short-range interactions, lambda v is well defined at the edge of the operator and outside, but it's not yet clear how to define a positive Lyapunov exponent inside the Lieb-Robinson cone. What is it that grows exponentially by a large factor, if anything, in fully quantum many-body chaos? This is an open question. Challenge for you guys. It's not obvious whether there is something, we need to figure out what it is here, or there really is no such thing and we need to show there's no such thing. It's not clear, right? And so that's a basic open question here. Okay, so that's pause of a little section. Any questions about that before I move to the next topic? No? Okay, so my last topic in yesterday's lecture is the emergence of dissipative dynamics from unitary dynamics. And so we just posted a recent paper here, Vedika Kamani, Ashwin Vishwanath, and myself. And so this is about how does irreversible dissipative dynamics, in particular diffusion or viscosity or things like that, how does this emerge from reversible unitary dynamics, right? And we have a nice model where you can really just do this very explicitly, which is, I find it satisfying. Okay, so the example we have is diffusion. So say we have spin a half chain, or a qubit chain, whatever, spin a half chain. And now I'm going to look at a particular operator, which I'm going to call Z sub r. Actually, it doesn't have to be a chain. This could be more than one dimension. So Z sub r is the local operator that is the Z Pauli operator at r, and it's the identity at every other site. So when I say Z sub r, what I mean is it's the Z at r and the identity everywhere else, which is always what you mean by that, right? But I just wanted to reiterate that. And now the total Z, which is the magnetization, is just the sum over r of Z sub r. And let's take a dynamics where this is conserved. And that's the only conservation law. So whatever the unitary time dynamics is, it commutes with the total magnetization. So we have a conserved charge, which is the Z component of the spins, right? And we have explicit quantum circuit models that do this in this paper. And let's say there's no other conservation laws, right? And if that's the only conservation law you have, the hydrodynamics you're going to get is diffusion, right? Because in order to get something more complicated, you need other conservation laws. Like if you have momentum conservation or other, you might get spin waves or something like that. But with no other conservation laws, you just get diffusion. If you just have a scalar that's conserved. Okay? And so now we have two conservation laws from a certain point of view. We have unitarity, which is the norm of the operator, the square, the sum over all basis states of the squares of the amplitudes. And then we also have this thing's conserved, which is just the sum of the amplitudes over just this very special set of operators, which are these observable local z's, right? Okay, so, and this second conservation law will constrain the spreading of these z operators, right? This conservation law will restrict their dynamics, right? Because you've got to conserve total z, right? Okay. Okay, and so given that we've got this special set of operators which are in the conservation law, we're going to separate our Pauli strings, our basis set of all operators, which we're calling Pauli strings, into the conserved operators, which are the local operators which are in the conservation law. So these are local operators. They're quite observable because they're just single-site operators, and their spreading is constrained by the conservation law, right? And then there's all the non-conserved operators, which is everything else, right? And these, most of them, are highly non-local and thus, in practice, hidden observables, impossible to observe because they're just too complex. And they're typically less constrained by the conservation law because they're not part of the conservation law, right? Okay? So let's now consider the initial spin operator z0, right? So this is one of the conserved operators, and we put it at the origin. So at time 0, my operator, its amplitude is 1 for being z0, and it's 0 for being all other strings. So it is one of the basis operators, which is z0. And then at later times, this will spread to z0 of t, and now I'm going to break that up into two parts. The conserved part, which is the local magnetizations, which now have amplitudes, which depend on t, right? And this started as a Kronecker delta at the origin, but now it's spread out. And then all the other operators, right? Right? So that's what this operator will become. And an important point is these are all observables, right? They're all one-site operators, readily observables, whereas most of these, once the operators start spreading, they become very complicated multi-site operators, and so they're mostly hidden in the sense, hidden in quotes, right? In principle, if you have an 8-site operator and you're a really good AMO experimentalist, like we heard yesterday, maybe you could actually measure it, right? But maybe for 8 sites. But no, maybe what if it's 32 sites, right? And at some point, it's going to spread to the point where even the very best experimentalist will not be able to measure it, right? Because we have an infinite system, right? And so whatever their ability is, you can spread past it, right? All right. Okay, so there's my operator. It has spread, right? Okay, and the full dynamics of this operator is unitary and reversible, right? So the full operator, its norm is conserved, right? And its evolution is given by unitarity. So nothing's hidden here, right? I've got every string mentioned there, right? But once strings over here become highly non-local, it becomes essentially hidden, right? And so what we can do is we can say, oh, the part of this which is beyond the capability of anybody to observe, let's just drop it, right? Because, right? It's actually a good idea not to do that immediately. Let it go even 20 operators further and then drop it, because it might go 2 or 3 operators beyond the experimentalist capability and then come back, right? But there's a very strong flow in operator space out towards complexity, right? And so you don't want to cut it, too close. You want to cut it enough beyond the capability such that cutting it, stuff coming back by chance is negligible, right? Right? And so that leaves a non-unitary dynamics of the observables, right? If you do that, right, which is a natural thing to do, just cut it at some point. You might do it softly, just sort of let them damp. Instead of a hard cutoff, do a soft cutoff. But it becomes non-unitary dynamics, right? And that, I think, is the basic story of how dissipative hydrodynamics emerges from unitary dynamics, right? it is reversible, but stuff gets hidden. And if you ignore the stuff that gets hidden, it's not reversible, and it's dissipative. Right? And so what happens here, actually, OK, so we can do this for a random unitary circuit where we do the whole thing analytically. And this part just diffuses. And it just, that's time there. So it just spreads like a Gaussian with a diffusivity. So that's the actual diffusivity of the conserved quantity, 1 over t to the d halves. Sorry about the cross of the t being missing. If you solve it exactly in one dimension, this is actually a binomial, not a Gaussian, but in the long time limit, a binomial looks the same as a Gaussian in most of it. So this is the observable part of the operator remaining at late times. Looks like this. And then you can ask, of the full operator, what fraction of its weight remains observable, right? And so that, to do that, we just square it and sum it. And when you do that, you see that it's vanishing as a power law, right? So the fraction of the operator that actually remains observable goes to 0 at late time. And so most of the operator goes into this other stuff which disappears. Disappears in quotes. Gets hidden is the right way. It gets hidden. Okay. So what is dissipation? Dissipation is the dynamic conversion of simple observable operators into highly non-local and thus hidden operators. Right. And like I say, we have a quantum circuit where this can all be done just analytically, simply. And so it's a nice simple picture. It's really nothing new, but it's just very explicit. Right. Okay. So that's the end of lecture 1. Any questions about this or anything else in lecture 1?
Can you relate this to entropy production rate? You can actually define an entropy. Yeah. I'm not sure I have thought about that enough to say anything very systematic about it, but yeah, that's the kind of things we're trying to. Yeah, obviously it's producing entropy. Losing information.
Yeah. Well, it's producing entropy if you only look at the observable part. If you look at the whole thing, it's not, right? And it also depends on which entropy you choose, right? But if you're doing von Neumann entropy, the whole thing isn't producing von Neumann entropy. But if you truncate it in this way, it is. Right? Yeah?
Does this need to be chaotic?
That's a good question. I'm not aware of a. Okay, so with the random circuits, in some sense, they're automatically chaotic because you're driving them in a random way, right? And so that's sort of. But with the Hamiltonian or Floquet systems, I'm not aware of any ones that are integrable, non-chaotic, and give diffusion, right? So. But this is a very good question. It's like, how important is chaos for this? Are there cases where you could have the whole story in a Hamiltonian system without chaos? That would be a very interesting example to think about. Yeah. Matt?
So when we think about like hydrodynamics emerging from like kinetic theory or something like that in this sort of.
You're doing this. You're doing this. Right? When you do the Boltzmann equation, you do exactly that. You just throw out all the correlate. When one particle scatters off another particle in the Boltzmann equation, there's all sorts of entanglement between the things, and you just drop it. Right?
But it seems like, you get these, maybe it's the same, but I'm not quite making the connection because there it seems like the degrees of freedom you're throwing out are microscopic ones, like the positions of all the individual molecules or whatever. But here what you're throwing out is like the long distance observables.
Not long distance, highly complex, highly non-local stuff. Stuff that involves products of many operators.
I see. So that's what keeps track of these correlations.
Well, that's where the information that gets lost in quotes. That's where it goes. It goes into very complicated operators, right? Well, no, but let's. Yeah, but like nowadays the atomic physics people, they don't coarse grain, right? They look at single atoms, right? Single ions, right? And so you don't need to coarse grain, and you shouldn't restrict yourself to coarse graining. Nowadays when you're doing many-body quantum physics, because many-body AMO physics, they don't coarse grain at all. They can access every degree of freedom, right? And so any degree of freedom or any 2-point operator or 3-point operator, that's observable, right? But the difficulty is when it's a 15-point operator, right? And then it's just to do that experiment, the fidelity goes down as e to the minus something times 15, right? And at some point, it just doesn't work, right? But yeah, traditionally people cut it, much earlier, right? Right? Like in the Boltzmann equation, you cut it immediately after the scattering, right? Right? And but that's kind of brutal, right? Right? Because of course, nowadays, people could follow those particles and see those correlations, right? And so.
So can you think of this as a kind of coarse graining?
In a certain sense, yeah. But it's not a spatial coarse graining. It's sort of a complexity coarse graining. It's locality. It's sort of the principle.
So is there a classical analog, or is this all about entanglement?
That's a deep question.
Well, is there a classical analog?
Well, there is a classical analog. So usually in classical physics, people assume you don't have precise measurement of the classical state. You have some uncertainty, resolution or something, and then, and you just can't see stuff beyond, below a certain resolution on the, and then you get entropy production, right? Because of that, which is a coarse graining in configuration space, right? Just from your resolution. No, yeah, connecting all this to classical is interesting, right? There's also another interesting point, which, I think to some people it's trivial, but it's not, which is, there's classical dynamics obeying Newton's equations, right, where there's no entanglement, right? But then if you ask, how do you get classical dynamics from quantum mechanics, if you believe the world is quantum mechanical, what you do is you make coherent states in classical mechanics, and you take the limit of h bar to 0 or whatever, right, large S, something like that. And those states, if you do their dynamics properly, they're highly entangled. So the classical limit is both infinite entanglement and zero entanglement, which is kind of a funny thing, right? So if you do what I'm doing here, or the entanglement dynamics I did earlier, you do that for semi-classics with coherent states, there's entanglement production. And you take the limit of large S, or the classical limit, the entanglement production doesn't go to 0. There's a lot of entanglement production. If you approach the classical limit from quantum, you don't turn off the entanglement production at all, right? And in fact, the total amount of entanglement gets larger. The closer you are to the classical system, the higher the entanglement. Right? And in some sense, classical physics emerges because the entanglement is so large that you can just ignore it, which is, it's a weird thing. Okay. So here's summary of lecture 1, just to remind you of the topics I talked about. So I talked about thermalization, a closed many-body system being a thermal bath for itself. I talked about entanglement dynamics, the local production of entanglement. I talked about many-body chaos, the Lieb-Robinson speed, Lieb-Robinson cone. I talked about operator spreading today, and emergence of dissipation, which is the hiding of observables. Okay. So my second lecture is about many-body localization. But are there any more questions about this topic before I swap? Yeah?
So how do additional conservation laws
They make it more complicated.
And eventually you don't have the diffusion, because in an integrable system you would have a lot of conservation laws, and that would
Yeah, I think. So usually with integrable systems, it's not that you turn up the number of conservation laws gradually to infinity, right? It's more, you have integrable systems which have infinite number of conservation laws because of some special property they have, and then you break that and the number of conservation laws goes down to some number of order 1, right? And and in between there, that's a whole big subject which is, being investigated and very interesting, but, it seems like you break the integrability, it just introduces a very long time scale, and the system does thermalize, that you have this long time scale regime, and that gives you pre-thermalization where there's some remnant of the integrability before it finally thermalizes. That's probably what happens, but this is still something that's, I don't think it's completely under control yet, but a lot of people are thinking about this and working on it. Okay, so let me just bring up the other. Whoops. Okay. Many-body localization. So as I mentioned yesterday, sometimes things don't thermalize, and one reason they might not thermalize, which is an interesting case to me, is many-body localization. Okay, so Rahul Nankishore and I have written a sort of basic review of this, which is in this paper here. Okay, so actually, right. So this is Anderson localization. In fact, right around just now is the 60th anniversary of Phil Anderson's paper, which I think was published in January of 1958, before I was born, but not by much. And that paper is about many-body localization. So he was thinking about spins in semiconductors, interacting spins. And so it was an interacting system, and the spin interactions were not super strong, and the temperature wasn't low. So he was working at reasonably high temperatures, and he was talking about thermalization. In fact, you read the beginning of that paper, it's about thermalization. It's like 50 years ahead of its time. And everybody ignored that part, because then he made an approximation of ignoring the interactions and doing the single particle problem, which is much less interesting. But then people spent 50 years working that out, because it's there's a lot there, and the many-body localization problem kind of got ignored, mostly. But it's where Phil started, because he was doing a spin model, just like we're doing now in many-body localization. So this is Anderson localization with interactions in highly excited states, meaning at energies that if the system did thermalize, would be non-zero temperature. Right? And just like the other stuff I was telling you about before, we often just study this at infinite temperature in spin models, because that's already very interesting. So systems, and then there's a phase transition between, so a lot of the models have a many-body localized phase and a thermal phase, a phase where it does thermalize and a phase where it doesn't, and then you have a novel kind of phase transition, right? So we have two phases, at least in the simplest approximation. A new type of phase transition. The many-body localized phase is a type of quantum memory where some local memory of the local initial state is stable to infinite time, right? And so that's sort of intriguing for possible quantum information storage possibilities, although it's not clear that'll ever be useful, but that's one of the interests. And then you also have the phenomenon that we've called localization protected order, where many-body localization can dynamically stabilize a long-range order, a topological order that's already present in the initial state, and make it dynamically stable.
even though the system at thermal equilibrium would just disorder, right? And so again, this is interesting. And one example of that is this thing that was mentioned yesterday, discrete time crystal, where one of the types of order would be breaking time translational invariance. Okay, so just like all of these problems, the simplest examples are spin chains. And I'm going to actually start with something that's absolutely trivial, but in fact, it contains the essence of it. Okay, so spin a half chain where all we have is fields on the z components of each spin, no interactions. Okay, so don't worry, I'm going to add hoppings and interactions soon, but for now, this is really trivial. But okay, so we could do this with a Hamiltonian, or we could also do a Floquet model, where this is somehow some Floquet operator that is equivalent to that. But I'll do Hamiltonians because it's more familiar. Okay, and this could also be viewed as a particle model where, say, down is no particle and up is either a fermion present or maybe a hardcore boson present. We could do fermions or bosons. The particle statistics so far has not had much, it doesn't seem to have much consequence for many-body localization because we're not talking about low-energy physics where the degeneracy is important. So either species of particle seem fine for, okay. And this could be realized by cold atoms in some lattice. So you put on a lattice and you put on random potentials on the sites and you make the barriers high so there's no hopping. And so you can set this up easily in the lab. Now, this, trivially, is an integrable system because every single one of these ZNs commutes with the Hamiltonian. Right? It's trivial. Right? So, and this is what we mean by many-body localization, is we have a set of localized conserved operators that commute with each other and with the Hamiltonian. Right? That's the structure of many-body localization to the extent we understand it. What is localized? The state is not localized, right? Because it's a many-body system. The state, every degree of freedom in the system has a state, right? And so the state's not localized. What's localized are operators which commute with the Hamiltonian. Okay? And in this case, they're just these ZNs, right? And so we have an extensive number of those, and they're all local operators, right? Okay? So that's a very simple structure. Okay, so for stability of this trivial MBL to hoppings and interactions, so now I'm going to say add some nearest neighbor interactions or hoppings. You want that these fields on the different sites are not equal, right? Because if two of those fields are equal, once you add a coupling, there's going to be a resonance between the two, and you're really going to get a lot of entanglement, possibly, right? And so we want what the atomic physicists call detuning, right? That these different Larmor frequencies are different, right? So there's no resonances. So once I start coupling these things now, there's no resonances, and that's the key, right? So you want, and there's two main ways to do that. One is to just make them random and drawn from a continuous distribution, and then the chances of them being exactly the same is very low. And so you can do it with randomness, and that's what Phil Anderson did in his localization paper, put on a random potential. But you don't need randomness. Randomness is not important for Anderson localization. What's important is detuning. And you can get detuning other ways, and one nice way, which is not random, it's perfectly deterministic, is put them on quasi-periodic. So if we're in one dimension here, we can just have these potentials be a periodic function of this, and if Q is irrational, it'll be quasi-periodic and it'll never repeat, right? And that makes localization nicely too. So you don't need randomness for localization, and there's a certain sense in which randomness is actually irrelevant for Anderson localization. You can see our recent paper about that. Okay, so what do we have now? We've got this thing. These fields are not, they're all different, right? Or if there are any resonances, they're rare. There's not very many of them.
And then we have some weak short-range hoppings and interactions, and let's say we're in 1D. Right? Now for the random cases, where this is random, the perturbative stability of MBL was shown by Bosco, Alainer, Altschuler in 2006. And it was this paper here which really brought this subject back to, well, it brought it to the attention of a wider community. And since then, this has become an active research subject, and particularly in the past maybe 7 years, very active. But this is a very important paper in getting the sort of modern era of many-body localization started. Now, you can have non-perturbative effects, and you should worry about non-perturbative effects. And we knew that, and John Embry is a mathematical physicist, and so he looked at this and actually went a little further than these guys and showed, didn't prove, because he had to make one tiny assumption, which is obviously true, but after 2 or 3 years of effort, he still couldn't prove it, so he just presents it as an assumption. But it's just like something nobody has any conceivable scenario where it's false, but he couldn't prove it. Right? And so he makes one assumption, and then other than that, he proves non-perturbative stability in 1D. So we should view that as proven, and that's Embry 14. But he could only do it in 1D. These guys, their argument is general, but this only works in 1D. And there are non-perturbative effects in higher than 1 dimension which may destabilize many-body localization. And I might get to that if I get a chance, depending upon the clock. Where's Greg? You're supposed to move the clock back. OK. For quasi-periodic, these perturbative arguments work, and we do numerics. And everything looks fine. And in particular, as I may show you, well, let me just say it now, MBL, many-body localization, is actually more stable for quasi-periodic than for random. Randomness is bad for many-body localization because randomness, by chance, makes resonances. Quasi-periodics got less resonances because things are put down deterministically, right? And so we can very clearly see numerically that MBL is more stable for quasi-periodic than it is for random. That's very clear. And so given that it's in good shape for random in 1D, it's in good shape in 1D for quasi-periodic. Although doing that mathematically is much harder. So randomness is actually easier for mathematical physicists than quasi-periodic. OK. Right. OK, so what happens when we add these interactions? So what happens is you just take the conserved operators, which were initially just these ZNs, and you dress them, just like you dress quasi-particles in Fermi liquid theory, except in this case, you dress them to make them completely stable. Right? When you dress quasi-particles in Fermi liquid theory, you're not making conserved quantities. You're just dressing them to make them more conserved, but they still have a lifetime. But here, you can dress them. And the dressing contains multi-site terms that have typical magnitude and probability of being large that fall exponentially with distance. So you dress them with just nearby stuff, products of operators, stuff like that, in order to preserve this algebra, right, that you had up here. Right? So the Pauli algebra is preserved. The things still commute. And these we call L bits, localized bits. Right? And so we call them tau sub n. And it's basically just this guy with enough dressing to preserve its commutation with the Hamiltonian with each other. And the details of how that works is not that illuminating. But that's basically what these guys proved, is that you can do that. Right? In order to do the unitary transformation from Zn to tau n, it's a shallow, a low-depth unitary circuit. Right? That's another way of saying it. Quantum information way of saying it. OK, so MBL is a type of integrability, very different from traditional integrability like beta ansatz. But unlike traditional integrability, it doesn't seem to be fine-tuned. Right? So traditional integrability, if you add some arbitrary short-range couplings to the Hamiltonian, you'll break the integrability. It's only very special terms that won't break the integrability. Whereas here, you change these fields a little bit, change these interactions a little bit. You will change the L bits a little bit, but the basic structure won't change. Right? So it's robust to short-range perturbations to the Hamiltonian. So it's a type of integrability, and it's really more robust than traditional beta ansatz type integrability. Right, and so because of this, MBL survives weak interactions, but it may have a phase transition to a thermal phase, which thermalizes for strong interactions, or if you add interactions which are too long range as well. So it also tends to be unstable when you add longer range interactions. Questions? Yeah.
So when you say that the particular periodic system, MBL, is stronger than the disordered system, so on which ground do you compare the positronic potential with the disordered potential? Because
The eigenstates in the many-body localized phase have substantially less entanglement, and the phase transition to the thermal phase is shifted to make the many-body localized phase bigger and the thermal phase smaller. So there's two clear criterion, which are very sensible ones, and this is a substantial effect in the numerics.
Okay. What I should be asking instead is that, okay, we know that for periodic positive-periodic potential, if it's less than a threshold, then even the single particle wave functions are not localized, right? Well,
Yes.
For
Yes.
localization,
Right.
for
Yeah.
Actually small disorder is localized.
Yeah.
So on that ground, that statement doesn't seem very
Yeah, you're right. I should have pointed that out. For the single particle problem, the situation, as he said, is exactly the opposite, right? If you do single particle localization in one dimension or two dimensions, an arbitrarily small random potential will localize.
Right.
So localization is more stable for the single particle problem with disorder than it is for quasi-periodic. But in the many-body problem, it's the other way around for reasons that, well, why don't I just skip ahead to that? Let's see, where is it? Yeah, no, I think I'll get to it. Okay, so, yeah. Yeah, I think I'll get to it. Okay, so we've got these conserved operators, which commute with the Hamiltonian, and then we can just take our original Hamiltonian, which was written in terms of the Bayer operators, and let's write it in terms of the conserved operators, and it looks like this. And so this is what we call the L-bit Hamiltonian. It's just an Ising model, right? Because these are the Z components of Pauli operators, and they all commute with the Hamiltonian, so the Hamiltonian can't contain any X or Y Pauli operators, because otherwise it wouldn't commute, so it only contains Z operators. Right? And so it's an Ising model, and it has 1 spin terms, 2 spin terms, 3 spin terms, etc. Right? And this is the dressing, and these guys fall off exponentially with the distance. Right? So that's what the L-bit, that's what it looks like in terms of the localized conserved operators. But remember, each of these operators has a footprint in space which falls off. Right? So these are not strictly local operators; they're localized inside some envelope which decays. Right? And the phase transition is basically when you stop, these L bits, they delocalize. You can't make them and have them be localized, right? So you can write this out, but the operators you're making are completely delocalized in real space, right? Okay. So there's a so-called standard model of MBL, which is partly my fault. I actually don't like it anymore, but because a lot of MBL is done numerically and by a lot of different people, it's good for different people to work on the same model so they can compare their results, right? And so that's why there's a standard model. It's not a good model, it's just a social convention, right? And it has features that I don't like anymore, but I'm partly to blame. Okay, so what is this? This is the Heisenberg spin chain with a random field along the Z direction at each site, and these fields are selected from the uniform probability distribution between minus h and h. Right, so it's a random field, Heisenberg spin chain, fields along the Z direction. It has conserved energy and it has a conserved total Z. And those are two of the features I don't like, because when MBL is not about conservation laws, it's about entanglement and unitarity, and conservation laws are just a distraction. And they get in the way of the analysis. And so it would be better to not have any conservation laws. But we didn't know that when we started. and this became a social convention. So this is, just like other things, there's many social conventions which are inappropriate. Okay, so this has a phase diagram that looks like this. Okay, so at h equals 0, this is another one of its bad features. At h equals 0, it's the Heisenberg spin chain with no randomness, and that's the problem where beta invented the beta ansatz. So that was solved in 1931, the first non-trivial piece of many-body quantum physics ever. And that's another bad feature of this model, because we don't want to have any integrability anywhere nearby, because that's just a distraction, right? Okay. So, and then there's for weak random field, it does thermalize, and ETH is true. And then, but if you put a strong enough random field, right? If obviously, if the random field is very large, we can ignore this term, and we're back in the case which is localized. And so you have the localized phase out here, which is where this term is big and this term is small, right? And over here, the L bits exist, and the ETH is false. And the phase transition happens somewhere here, around 4 or 5. That gives you an idea of how accurately we know it. I don't even want to put error bars on it, because we don't know how to put error bars on it, because we don't really have a good theory of it. There's much uncertainty in the location and the nature of this phase transition, and even could there be an intermediate phase? There's a bunch of people who would like to have an intermediate phase, although it's not clear exactly what that would be. But I think there's still a lot of room for an intermediate phase to the extent we understand this problem. Okay, so but in practice, okay, so this is the phase diagram. This is a sharp phase transition. Here, these are sharp distinctions. ETH true, false, L bits exist. Here they're, localized L bits exist. Here they don't. But in practice, it looks more like this, we think. There's a thermal phase, and there's part of the thermal phase where it actually thermalizes on accessible timescales. And then there's part of the thermal phase where the thermalization is extremely slow, so it looks localized, right? But it's actually going to thermalize at some very long time. But that's hard to show. And then there's the phase transition to where it really is localized. In the eigenstates, really, there really are L bits, and it's localized forever, as opposed to almost forever. Right? And that's the sharp distinction. This is just a crossover, which depends on how hard you're working, right? Right. So this is the real situation, and most studies many studies of MBL end up focusing on this region here, and sometimes this doesn't even exist, and it's all just this crossover, right? And so one open question is, can there actually be an intermediate phase as opposed to just a crossover, right? This is kind of like the glass transition. Is it really a transition, or is it just really slow down, right? So is there some phase which is neither satisfying ETH nor having localized conserved operators, right? Is there, it's actually a sharp distinction. That's an open question. I don't see any reason to believe there is an intermediate phase, but the evidence, is not that strong. Or is it just a very slow part of the thermal phase? So, yeah.
So when you're talking about the phase diagram, are you focusing on the middle part of the spectrum, or everywhere in the spectrum?
Well, so there is an argument that this phase boundary does not depend on the temperature, right? And so perhaps I'm looking at the whole spectrum if we believe that argument. I mean, the whole spectrum if I believe that argument. Now, this crossover does depend on the temperature. So if I move, so this phase diagram is the phase diagram at infinite temperature, on a typical state, right? Now, this crossover here certainly moves as you go towards the ground state or towards the highest excited state. To lower entropy, you get more localization when you go to lower entropy states, right? Now, whether this phase transition moves or not isn't clear, right? And there are arguments that it doesn't. But yeah, when I show the phase diagrams like this, I'm talking about, at one particular energy, typically infinite temperature. But yeah, that's one of the open questions, right? Does this phase transition depend on the energy density, or is it independent of energy density? And there's arguments
There's theoretical arguments that it doesn't depend on the energy density, but then the numerics suggests that it does. But I think the numerics is mostly just looking at this crossover here, which does depend on the energy density. Right?
But whether there are orbits or not cannot depend on the energy.
Yes, right. Yeah. If the phase transition does depend on the energy density, then there must be an intermediate phase. Right? Because whether there's L bits or not, that's just a property of the operators, the full Hilbert space. Exactly. Very good point. Yeah, I should have said that. Okay, so now to get to one of these non-perturbative arguments, so I want to say a little bit about non-perturbative rare region or Griffiths effects. And we wrote with Sarangopala Krishnan, we wrote a couple of papers about this here. There are interesting Griffiths effects in both the thermal phase and in the many-body localized phase, but I'm going to focus today on the Griffiths effects in the many-body localized phase because they're, in some sense, more important and also less well understood, but more interesting. Okay, so in the many-body localized phase, and now we're talking about the random case. Right? So in the random case, just by chance, you could have a rare region, right? And so this rare, so here's my whole sample, and say we're in more than one dimension, we're in d dimensions. So I'm talking now about more than one. Well, I'm going to talk about both one dimension and higher dimension. So here's my sample, and here's a region where just by chance the random fields or the disorder, whatever we have, happens to be small, and this region actually wants to thermalize because it's less disordered. Right? That's what a rare region is. It's just by chance that the configuration happens to be, it wants to be in the other phase. But it's not a big system, so it can't really do a phase transition. Right? Okay, so RR is rare region. It's a rare region of radius L where by chance the randomness is weak. Such regions do occur for any finite L in an infinite system with some density which is exponentially small in their volume. So they're there. In an infinite system, rare regions of any size are there in a random system for a typical probability distribution of the disorder. Now, the most important rare regions don't have to be compact things like this. They might be something more fractal-like, but let's do this for simplicity because the argument is already there with these guys. Yeah?
So when you say randomness is weak, could you be more quantitative about what that means?
Well, weak enough to be on the other side of the phase transition, right? So here's my, okay, so we're over here in the MBL phase. And this is say the RMS field. And then in this particular patch, just by chance, the RMS field is, let's say, down here. So you're in the thermal phase. Locally, you're in the thermal phase, but you're just a finite system, so it's not a sharp transition.
How large does this rare region need to be? Because if I choose H randomly between minus H, some minus capital H plus capital H, I will always find some parts
Where this happens, yeah. That's the whole point. Stuff happens. Yeah? If it has a non-zero probability, it will happen. It just might be rare. That's what rare means. It's got a non-zero probability, but a very low probability. Right? And the probability goes exponentially, it's exponentially small in this volume. And I'm considering any volume, and I'm particularly interested in large volumes. So rare events, really rare events. Large deviations, rare events. Right? That's why these things are non-perturbative. Because you don't get stuff like that in standard Russian perturbation theory, right? Right? There's no graphs that look like this. Okay, so if we ignore these rare regions, just cut all the bonds between the rare region and the rest of the system, so find all the rare regions and cut them away, then everywhere else we can make L bits and we'll have a Hamiltonian which looks like what I showed you. Because everywhere else it's well localized, right? Okay, so now we've got this rare region which has complicated local eigenstates, and then everywhere else we've got L bits, which are nice local spin-like operators, right? The rare region contains, if it's of radius L, it contains of order L to the d degrees of freedom, and it has a many-body level spacing that's exponentially small in its volume, right? And let's choose some length unit, so there's a 1 there, right? So I'm setting my length unit at this point here. And so for large L, that's a big Hilbert space, and locally the eigenstates will satisfy ETH, and it'll look like a thermal region. Right?
but with a finite level spacing, right? Exponentially small. Okay, so now let's consider an L bit that's not in the rare region, but at some distance r from it. Okay, so there's the picture here. Here's my rare region. And the place where the disorder is actually weak, I call the core. So that's the place that's actually rare. Then there's this region around it we call the periphery, which is just typical places, and there's L bits there. But the L bits are coupled to the core with a coupling that's big enough so that in the end they're going to get entangled with the core. Okay, so let's go through that. So only the core has weak randomness. These places don't. And now we have a coupling between this rare region here and the L bit. And that's going to have a matrix element which is going to fall off exponentially with the distance, right? Because now we can do perturbation theory out here because it's localized. And we're just going to pick up, you know, this thing is rth order in perturbation theory, and so it's going to be exponentially small in r with some decay length. So this zeta is some decay length, which comes in for the typical interaction of an L bit with this guy at distance r. Okay? So this is the matrix element for processes which flip the L bit and rearrange the state of the core. And let's just do a Fermi-Golden rule estimate of the lifetime of this L bit, right? And so now what do we have here? We got the L bit here. It's just got two levels, up and down, and they're split by something. And here's the core, and it's almost a continuum, right? And if the lifetime of this L bit is short enough, these lines will be broad compared to the spacing of these lines, and we can call this a continuum, right? And Fermi-Golden rule should work, right? And you do that, and the lifetime goes as the matrix element squared, right? And so we get a lifetime which is exponentially small in the distance. And that's valid provided the lifetime is big compared to this level spacing, because this came from assuming that this was a continuum, right? And it isn't a continuum. It's only a continuum on certain energy scales, right? Okay? So as long as you calculate the lifetime of the L bit assuming this is a continuum, and if you get the answer, the line broadening of the L bit lines is broad compared to this level spacing, you believe it, because that's the regime where this argument should be valid. And under this circumstance, the actual eigenstates, the L bit gets entangled with the rare region. And so the effective bath, due to this core, actually contains the entire periphery. Every L bit out here that gets entangled with the core is actually part of the rare region now, right? Because now the rare region is this thing which has an even bigger Hilbert space, and it's got an even smaller level spacing, right? And so the size of the periphery is set by the farthest out L bit that does get entangled with the core, and that's this here. Here's the lifetime of that L bit, and here's the level spacing of the whole thing, including the periphery, right? So this, right, so we call it an avalanche, right? So you've got the core, it's thermal. It thermalizes a region around it. Now it gets bigger, it's got a smaller level spacing, it can thermalize even further out. And it just keeps going, and the question is, does this stop? Right? Now, calling it an avalanche is very misleading because it goes at a rate which falls off exponentially with the distance, right? So it's more like climate change than an avalanche, right? It's like, or even slower than climate change, right? But we call it an avalanche because so it gets going, and the question is, does it run away or does it stop, right? Right. Okay. And if you solve this, that's just this equation here, which is a reasonably simple equation. And if we do this in 1D, and this decay length is less than 1 in the units I chose earlier, you can solve it, and you get that the radius of the periphery is this formula here. Here's the radius of the core, and the periphery is larger by this factor, as long as this denominator is positive. That's fine. And the avalanche does stop in 1D. Right? And we can actually test this numerically in 1D by just by hand putting in interactions which fall off exponentially with some decay length. And you can see very clearly in the numerics that once you go past this threshold here, the avalanche does run away. Right? And so that's been tested and really works numerically. And it's actually surprising. Unlike most numerics in MBL, which is very murky and hard to interpret, this one actually was really quite clear when we did it. Right? We knew what to do, and then we did it, and it's actually surprisingly clear, even to, right, compared to typical MBL numerics. Okay. right? And so in 1D, MBL phase can remain stable as long as its decay length is short enough. And that's, of course, what Embry proved, so it's not surprising that it's true. But if you go beyond this decay length, as they emphasize in this paper here, the avalanche doesn't stop, and the MBL phase is unstable, right? So when I say you need short-range interactions for MBL, so usually when we say short-range interactions, exponential decay is fine, right? Usually when you say I need short-range interactions, this is true. Exponentially decay is fine, and there's no constraint on the decay length, usually. But in this case, there is, right? Exponential decay is fine only if it decays fast enough, right? Stretched exponential is no good. It'll thermalize. And even exponential decay, it'll thermalize unless the decay length is short enough, right? So the MBL phase is very fragile because of this effect that entanglement wins, right? The MBL is coherence, the thermal phase is decoherence, and the phase transition is a battle between coherence and decoherence. And in that battle, decoherence has the upper hand, right, by an enormous factor. Decoherence always wins. It's a rare exception when coherence wins, right? And that's why atomic physics, experimental atomic physics, or experimental quantum physics is so hard, is because decoherence almost always wins, and they're just constantly fighting against it. And MBL is similar. MBL is coherence. The thermal phase is decoherence. The thermal phase has the upper hand. MBL is very fragile because stuff gets entangled. OK, was that a satisfactory answer to your question? So this is why disorder is bad for many-body localization. There's no such instability for single particle localization because you don't have those kinds of rare regions, right? Yeah.
So that one was the unit of lattice spacing or the
It was in the unit I set back here. When I set the level spacing, the many-body level spacing of a rare region of radius L is e to the minus L to the d, and I put a 1 there and set the units. So it has to do with the entropy density. I think it's units where the entropy density is been set to something, 2 or a half or something. If you look in this paper here, it's done properly. There's some tricky stuff with the factors of 2 in the Fermi-Golden rule argument. Also, it's easy to get a factor 2 wrong there.
Is it the order of the localization?
What's the localization length?
Outside the...
We don't have a good definition of the localization length. Yeah, nobody has made a good measurement of the localization length in the MBL phase. And basically because we don't have a good definition really, and there's not much to see, for reasons that I would tell you about if I had about 25 more minutes, which I don't.
How much? Wow. As a compromise, maybe another 10 would help.
Are you? You really? Well, let me just finish this here, since I'm doing it. So that was 1D, but if we do more than 1D, we have this equation: r equals zeta r plus L to the d. And this function goes up faster than this function as a function of r, right? Because this has got power bigger than 1, and this has got power 1. And this function gets a head start because of the L, right? And so if L gets too big, it has a head start, and this guy never catches this guy, and there's no solution, and the avalanche runs away. So in more than one dimension, if you do a large enough rare region, the avalanche runs away, right? And it doesn't matter what zeta is, right? If zeta is small enough, you just have to go to a larger L, and it'll run away. So these guys argued there's really no true MBL phase with randomness in more than one dimension because of these rare regions. So the rare regions thermalize the whole system, but very slowly, right? So when I say there's this intermediate regime where it looks like MBL, but it probably ultimately thermalizes, that's this kind of stuff here, right? It might thermalize on something, orders of magnitude beyond the age of the universe, but it's really not a phase transition. It's just very, very slow. OK, but if we do the non-random case, quasi-periodic detunings, not random, you don't have these rare regions, And so we think the MBL phase is probably stable in more than one dimension as long as you don't put in randomness, if you just have quasi-periodic. And in fact, a lot of the cold atom experiments on the MBL phase, they don't put randomness, they put quasi-periodic potential, because that's much simpler. You just put a laser on, right? A periodic potential. You put on a laser whose wavelength is incommensurate with your optical lattice, just two incommensurate optical lattices makes quasi-periodic. It's very simple, right? And so it's actually nice that the easier thing to do in the lab is more, the MBL phase is more stable than the harder thing. In 1D, the numerics show the MBL phase is more stable. This is what I said earlier. So we have this paper comparing really head-to-head on the same basis, quasi-periodic to random, and showing that the quasi-periodic is, the phase is more stable and the eigenstates are less entangled. And we believe that difference is due to these rare region effects. We don't actually demonstrate that explicitly because we don't know how to actually, in a typical sample, we don't know how to systematically find these rare regions. We've made various efforts, but nothing's ever really been satisfactory. But let me, since my time is up, let me just wrap up. Okay, so I talked about many-body localization. I told you it's a type of integrability which involves localized conserved operators. So you don't, unlike single particle localization, you don't localize states, you localize operators. And these are eigenoperators that commute with the Hamiltonian. So they're eigenoperators of the dynamics, right? And those get localized. Important point on many-body localization, well, actually for both my lectures, many open questions remain. These are hard problems. I told you about the non-perturbative rare region effects, which certainly by the argument I gave you, destabilize the many-body localized phase in the presence of randomness in more than one dimension. And like I said, in one dimension, those arguments have been pretty well tested numerically, and it looks good. Doing serious tests of it in more than one dimension is a real challenge, because it's really just exact diagonalization stuff, and the finite size effects are terrible in more than one dimension. And then the part I skipped, because we're out of time, was to tell you the phase transition is very, very interesting. It's a novel type of quantum phase transition occurring in highly excited states, a quantum phase transition occurring in one dimension at infinite temperature. So it's a very different type of phase transition. It's not an equilibrium phase transition. It's purely a dynamical phase transition. And so that's something that's being explored. It seems to have two universality classes in 1D, one with randomness, which is governed by an infinite randomness fixed point in a renormalization group treatment, and then the other one being the quasi-periodic case, which is not random. But when you add randomness to the quasi-periodic, it's relevant. If you do the Harris argument, you measure the exponents for the non-random problem, they don't satisfy the Harris criterion, so therefore you add randomness and it flows away to stronger randomness, and it seems to flow to infinite randomness. And we have an RG picture of this transition. So it's an RG picture, which means it's a heuristic RG, inspired by the strong randomness RGs that Daniel Fisher developed for one-dimensional ground state problems, where they're really systematic. But here we can't really so far make it systematic, but it's it might capture a lot of the physics, but we're not sure. So that's what you missed.
Thank you very much, David.